All right. Okay, welcome everyone. Um, Today we are here to celebrate Jonathan's promotion and tenure. So Jonathan Scarlett is an associate professor in the Department of Computer Science and Department of Mathematics, National University of Singapore. His research interests are in the areas of information theory, machine learning, and high dimensional statistics, with a particular emphasis on information theoretic methods, foundations of data science problems. Previously, Jonathan received the B engineering degree in electrical engineering and B science degree in computer science from the University of Melbourne, Australia. Between 2011 to 14, he was a PhD student in the signal processing and communications group at the University of Cambridge. And between 2014 to 17, he was a postdoctoral researcher at Lions EPFL. And today he's going to tell us about algorithms for group testing.
Okay.
What do you, John?
Thanks, Divesh. Thank you very much. Okay, thank you. So I'm going to talk about group testing. This is something I kind of got into half by accident while compressed sensing was popular. It's kind of related to compressed sensing, and yeah, kind of stayed there for, I don't know, almost 10 years now. So it's been one of the main topics I've focused on for quite a while. And yeah, I'll give like some sort of history, some old results, and some new things. Some of you may have actually seen an older version of this talk. Hopefully you can still refresh your memory, or maybe you've forgotten a lot of it. And there's some new stuff in here as well. Okay, I'm on slide 0 and I've already made a mistake. That's the wrong event and date, but yeah, let's hope there's no more mistakes. So yeah, let me introduce group testing with a toy example. So imagine we have a bunch of flasks and we're trying to test which ones are contaminated, or you could do this in like a medical scenario, like these are like blood samples and you want to see who's infected with something and who's not. Okay, and it's not this easy. You can't just look at the picture and see the color. Like we imagine that these all look the same and we don't know which ones are which. So yeah, we suppose we have a testing device and like we can put liquid in a testing device. It'll tell us whether it detects contamination or detects disease, whatever you're trying to detect. And yeah, naively, you just do that once per item or once per flask in this picture. And the idea of group testing is actually doing things one by one could be highly suboptimal. So perhaps you could actually find out what's contaminated, what's not, with much fewer than one by one testing would give. This picture doesn't really show that, but as an example, in the second test, we say you could take a pool of 3 items. So we take these 3 liquids, we mix them together a bit, and then we test the mixed liquid. And if that test comes back that there's no contamination, then at least if the test is reliable, that one test will tell us the status of the 3 items rather than just, rather than doing 3 tests one by one, we learned in a single test that those 3 are all clean. Okay, and then of course, if it comes back contaminated, it's more ambiguous. Okay, so if you test 5 at once and it comes back contaminated, you don't know whether it was all 5 or one of them or 2 of them, as in the picture. So maybe you'll need further testing to resolve such uncertainty. Okay, so yeah, this arose in the 40s. It was for blood testing for disease. It's also, most recent big application was also medical testing, because it was actually used for COVID, at least like a very simple version of it was used in COVID testing before we had like the rapid tests, like when PCR tests were very expensive and limited. But it's also just like an abstract sort of combinatorial or sparse recovery problem, and it has all sorts of other applications as well, which isn't really the focus of this talk. But yeah, medical testing is maybe where it started and where it's been popular, but there are many other applications. We want to figure out. We're trying to perform tests to figure out what's clean and what's contaminated, or which individuals say have a disease and which don't.
Right, but it's not a sample. It's all. You need the answer for all.
Yeah, there's different recovery criteria, but we'll say like we need to get everyone's status correct. Yeah, that's the simplest criteria that people consider. Okay, so we can sort of convert that picture into a more abstract and mathematical and compressed sensing type looking problem, or sparse recovery. So everything in this problem is binary. So the terminology people use isn't from medicine or from contamination. The terminology used is usually from fault detection. So like we think of these things as items, like in health applications, they would be individuals. And we think of these ones that are contaminated or infected or whatever you want to call it, we think of them as defective. Because yeah, in some of these fault testing applications, you can like test for defectivity in groups as well, and then it's the same problem. So yeah, we'll sort of adopt the terminology from testing defects, but you know, you could easily just replace items by individuals and defectives by, you know, sick people and so on. Okay, so here's the picture. I've shaded, just as an example, I've shaded 3 here to say that 3 items are defective. And we can represent tests using a matrix form. So think of each row in this matrix as a test and the shaded ones as being who's included in that test. Okay. So we have a bunch of tests. We have a bunch of people included in each test. And according to how I described the testing outcome, what we get is kind of an OR operation. So we get an outcome of 1 whenever there's at least 1 defective item in the test, or you know, or at least 1 infected individual, whatever you want to call it. Actually, in this first test, all three of them are infected or defective. But say in the last test, there's only 1 defective, but that comes out positive as well. So we have no distinction on whether it's 1 or 2 or 3 or more defective in the test. It's just 1 if there's any, and 0 if they're all non-defective. Okay, so yeah, this is the more abstract sort of sparse recovery problem. And we're sort of interested in cases where defects or infections are rare. So we're thinking of like a sparse setting where there's relatively few, say shaded, I'll call these 1s. So it's relatively few 1s in this vector, and most of them are 0, like most of them are normal or non-defective or non-infected. So
The sparse vector is worst case or average case?
I'll talk about that. So my talk is more about average case performance guarantees, and there are other studies on worst case. And the deterministic versus randomized can matter a lot. So yeah, my talk is more on the probabilistic viewpoint. So I'm gonna say that the set of defective items is uniform, like we don't have any prior knowledge. There's P items in total, K of them are defective, but it's uniformly random. So we have no idea which K. You could also do like IID, like everyone is independently defective with some probability, and it's a very similar model. Exactly, yeah. You could have fixed arbitrary S, and then you could say randomize the test matrix. If you sort of randomly shuffle your columns, it's like making S uniform anyway. So yeah, having uniform S is not that fundamental. Yeah. Okay, so we also have to, yeah, there's also like different models for like given what I described as the noiseless test outcomes. Like the noiseless test outcomes would be an OR operation. So yeah, this column of outcomes is the OR of these 3 columns highlighted in red. But of course, sometimes tests are not perfectly reliable, so we may want to model noise. Here I've just like shown like an additive, or it's like modular to arithmetic addition. So like if this Z was like a Bernoulli, it would just be like the noise gets, the test outcome gets flipped with some probability. And there are more sophisticated models as well. Like you could have things where like the more defectives are in the pool, the more likely you are to get a positive, or you could have things like dilution. If your test size is too large, maybe it dilutes the infection you're trying to detect and so on. But we're keeping things relatively simple in this talk. Okay, and yeah, adaptive versus non-adaptive testing will be important. I think I'll explain that more in a second, but briefly, non-adaptive is where you design this whole matrix in advance before seeing any outcomes. Whereas adaptive would be where like you see the outcomes and then use those outcomes to design your next tests. So you're sort of sequentially designing based on what you've already seen. So yeah, I think I'll come back to adaptive and non-adaptive soon, but okay, here's kind of what Devesh asked. Like, so there's various recovery criteria. I'm going to take a sort of randomized probabilistic view and just say we're interested in the probability that we don't recover the full set correctly. You could make this stricter and ask for 0 error probability. That's okay, in the noisy setting, maybe not, but in the noiseless setting, that is kind of feasible. You could go less strict and say, I want to recover 99% correctly or 90% correctly. So yeah, this is kind of sort of in between. It's like strict, but not super strict. And this is mostly what I'll focus on in this talk. And we're performing mainly asymptotic analysis because the non-asymptotics can get very messy, but asymptotic results can come out very nice. So we're kind of looking at what happens in a large system limit. N is the number of tests. We want to get error probability approaching 0. And there'll be some relationship between N, the number of tests, and like K and P, the number of defectives and number of items. So they'll all have certain scalings with respect to each other, which we'll see shortly. So yeah, in a noiseless setting, you can get,
Is something that is n has to be large.
we're looking at the large N limit. But
But shouldn't n be small?
in some applications, yeah, like in some of these DNA applications, like you do 96 tests at a time
I
specifically.
mean, you just want to have a small number of.
Yeah,
tests.
so you know, the theory may be a little bit limited in that sense. Like if you get this asymptotic theory, it may not apply there. Some of the test designs though, like do transfer very nicely to small n. And maybe not in this talk, but some of the theory is also like much less asymptotic and can tell you something about smaller sizes.
Because, I mean, the point was that in practice, n cannot be large.
In some applications,
Going to
n,
the limit, like,
in some applications, n is really large. Like in communications applications, n can represent like the number of possible bit strings going over the network, and that's like exponentially large. So like
close there.
n could be large, and I think in DNA applications, n can be really large. Like it varies on the application. Yeah. Okay, so we basically want to get upper and lower bounds on how many tests we need. So sufficient condition, like there's some algorithm that can get error probability approaching 0 when n is above some threshold. And we also like, I'm from information theory background, we like having necessary conditions. Okay, not only information theorists, TCS people like those as well. Necessary conditions stating that error probability, okay, I'm going to say error probability goes to 1 when your n is too small, and you could also say not necessarily 1, just your error probability is, I don't know, at least some value like 0.1, but without too much effort, we'll get the stronger result saying error probability actually goes to 1 if you have too few tests. The scaling turns out to be k log p over k, or sometimes k log p, and we'll see why in a second. But in this line of works, we're actually very interested in the constants, which is, you know, not always the case because it's not always that feasible, but this is a problem where you can actually get precise constants. And so we are specifically interested in this sort of value of CNC prime and hopefully getting them to match each other. So really getting a sharp asymptotic threshold, including the constant. K is number of defectives and P is the total number of items. So this, okay, I've got the intuition down here, like this K log P over K is just basically log of the number of possible defective sets. Like out of P, you're choosing K. And if K is much smaller than P, then log P choose K is basically this K log P over K. Okay, so yeah, again, linking to information theory a bit, like information theory talks about communication rates over a channel. If we represent the constant in this way, like 1 over C times sort of this prior uncertainty, then we can basically interpret these C or C prime as bounding how much information we learned per test. Okay, so like if we had n tests and the prior uncertainty was k log p over k, then this C, when you just rearrange things a bit, the C basically represents, yeah, prior uncertainty divided by number of tests, and therefore it's representing how much information you're learning per test. That normalization will be nice because like it'll mean like 1 is the maximum. We can't learn more than 1 bit per test because the test outcomes are binary. And we'll get like these constants going from 0 to 1 instead of like 1 to infinity or something like. So yeah, normalizing this way turns out to be a bit nicer, and this rate is interpreted as how much we learn from each test. Okay, so here's 2 like defining features that I'm going to focus on a lot. Actually, one of the defining features was like the recovery criterion, like, do you want to exactly recover S? Do you want 0 error probability? That's also important, but I'm just focusing on small error probability. Just as a side note, if you want 0 error probability, you need more like k-squared dependence. So you can get 0 error probability if there's no noise, but you pay a big price, like k-squared instead of k. So let's not focus much on that. Let's focus on these criteria here.
Just before you go on.
Yeah.
Does this connect to experimental design in statistics where you know?
Yeah, I think there's been some, I think some of the, even the really early works in Russia made that connection. Like, I'm sure they even had like experimental design in the, I guess not. Like, I'm not an expert on that, so I wouldn't know exactly. But I'm sure there's some of the early Russian works which literally have like screening and experimental design in the paper title. So they obviously saw some connection. Max?
I mean, it's max of that kind of. But I suspect the details differ.
Well, I don't know if they would always, I don't know if they would always have like an OR operation, for example. They might have more general functions instead. Okay, so yeah, here's the criteria. Like noiseless is where you just have OR, like if there's a defective in the test, you're 1, otherwise you're 0. But noisy could mean where, like, say, every test gets flipped with probability, say, 5% or 10% or something. You could have adversarial noise, but everything's sort of more random in this talk. And yeah, adaptive versus non-adaptive. So can you design tests based on past outcomes, or do you have to test you have to design all your tests in advance and then implement them all at once? Non-adaptive can be really preferred, like especially in things like medicine, because testing can take a lot of time, and like you don't want to be taking a lot of time, then redesigning, then taking more time. Like it's often really beneficial to be non-adaptive and be able to run them all in parallel. So yeah, I'll try to go roughly in like a historical order of how things developed. And noiseless adaptive was solved a long time ago, at least solved in like an asymptotic sense, or like you could even get good non-asymptotic bounds here, but yeah. Basically, this is a well-understood scenario, noiseless plus adaptive. And it's one of the like easier cases where you can have simple, very explicit algorithms. Before I get to the algorithm, let me just state this impossibility result, kind of formalizing the intuition I mentioned before. So the claim is that for any algorithm, this is just noiseless. So for any algorithm, you need to have basically k log p over k tests, base 2 log. Otherwise, you're going to get a high error probability as p and k grow larger. Think of this as holding when k is much less than p. Otherwise, maybe it's a bit more subtle. Okay, so the argument's really simple. Like if you have n tests, then there's 2 to the power of n possible outcomes. But basically, you need to get a different sequence of outcomes for every possible defective set, because we're trying to recover the defective set perfectly. So yeah, everyone should have a different sequence of outcomes. But there's p choose k of those. So yeah, p choose k possible sets, 2 to the power of n possible outcomes. So we need this inequality. Otherwise, 2 of them would give the same outcomes. You wouldn't be able to distinguish them. And yeah, if 2 to the n has to be at least p choose k, you just like rearrange and get n should be like log of p choose k, which is, okay, if k is small, it's like k log p over k. So yeah, that's a very simple argument. I'm being a bit informal, but it's also very easy to formalize. And the reason for putting that claim here is so that I can compare it to what's achievable by this algorithm, which is basically the same threshold. Okay, so if you have k much smaller than p, like formally, like it's like sublinear, then there's this adaptive group testing algorithm. You don't even have to have error probability. So I said 0 errors gives you k squared dependence. That's in a non-adaptive case. In the adaptive case, you can get 0 error and actually match this k log p over k. So yeah, in adaptive case, 0 versus non-zero doesn't make much difference. You can even just get 0 error probability with this algorithm. Okay, and here's the algorithm. Generalized binary splitting from 1972. Here's a version at least that knows k. If you don't know k, you could use a few tests to estimate it, at least in the adaptive case. So let's just say k is known. It's not that important. I'm going to split the p items into groups of size p over k. And then I'm basically going to do like binary search type subroutines to identify one defective at a time on these groups. So yeah, here's a set of size p over k. I can test the whole group. I'm using red to mean that there's some defectivity is detected. So I test the whole group together. I get that there's some defective outcomes, so I can keep searching for that defective. So maybe I test the left half. If the left half comes out non-defective, then I know the defective must have been in the right half. So I don't need to test both halves. Like I could just test the left half, and then once it's non-defective, must have been in the right half. Then I can just keep splitting in half. Okay, I test the left half, this time it's defective. Again, I test the left half, this time it's non-defective. And then if you keep splitting in half, you'll get down to one item, and that item will be defective. Of course, that might not be the only defective in that original P over K set, but that's not such a problem. You can basically like take out and remove the item you found, and then just go back to the start. So yeah, just go back to step 1. Maybe this time you test and everything's non-defective, and therefore you can stop worrying about that subset and move on to the next one. I guess, yeah, very simple, kind of just like binary search on these carefully chosen subset sizes. And yeah, basically you get k log p over k because there's log of P over K steps here. And you have to do it K times. Maybe you have to do a few more tests to figure out, I don't have to search this part anymore, but those extra tests are like second order terms. They factor into this epsilon. Okay, so yeah, very simple and explicit algorithm there. Any questions?
So if you want the exact algorithm based on n, then there's probably a lot of sub cases, depending on exactly what the n is.
Depending on n, I'm setting n to be. I'm saying this algorithm uses k log p over k. So yeah, how the numbers come out will depend on p and k. But you know, k log p over k is pretty. The dependence on p is really mild. So the dependence on total number of items is really mild. The dependence on k is more like linear, so that.
Right, I mean, depending what n is, you can't exactly do binary search and so on, so.
Well, yeah, maybe you're flipping the problem around. You're saying if you fix n instead of here, I'm fixing k and p. I'm fixing k and p and saying
Right.
what n needs to
Yeah,
be.
thinking of picking n.
If you fix n, you might be unlucky. You might be in this regime where you just have too few to have any hope of doing anything meaningful. Then you might have to start talking about like approximate recovery, like getting some of them but not all. So if you want to get them all, you really need this k log p over k. That's the way we're thinking about it. Okay, so next is noiseless and non-adaptive. This non-adaptive is really beneficial when you want to run things in parallel. This is a lot harder to get the exact constants of, and this from like, I don't know, 2015 to 20 was like the main focus, at least by people around my community. So yeah, in non-adaptive setting, we want to design this whole matrix in advance. So we obviously can't do this splitting type approach. That's very adaptive. And you know, anyone that's done randomized algorithms or information theory will probably pretty quickly think of, you know, randomized approaches. So it's actually a very good design, it turns out, to just randomly choose who's in each test. And the simplest way would be like IID, just like generate all these matrix elements IID. So you just randomly say who's in each test and who's not. You have to be careful with the probability. So like, what's the probability I put someone in a given test? And a reasonable probability is like 1 over k. The reason being, like, you know, you want to get tests with like roughly 1 defective in them, and that will be true on average with this choice. In some cases, a better choice is a bit lower, like around 0.7 over k. But you know, in terms of scaling, you want it to be roughly like 1 over k. Okay, so here's some simple algorithms before we get to like optimal thresholds, which is a fair bit harder. Here are some observations that lead to simple algorithms. One is that if you're noiseless and you get a negative test, you immediately know that everyone in that test is non-defective. Okay, because 1 defective would always cause a positive. So if it's negative, they all must be non-defective. Once you've declared a bunch of items non-defective, like definitely non-defective, you'll have a bunch of things which maybe have not yet been declared. You could call those possibly defective. Okay, so the possible defectives are like a superset of the defectives, but they may be a strict superset. And then this third observation is, if there's a positive test and it contains 1 positive defective, then we can upgrade its status to definitely defective. Okay, because yeah, there's only one, the test is positive, there's only 1 thing that could have been positive, therefore it's definitely defective. I think I should have said a positive test. Okay, if a positive test contains only 1. Okay, but by default, it must be a positive test anyway. So yeah, we can get some items that are definitely non-defective, some that are definitely defective without much thought. And this leads to 2 simple algorithms. The naming of comp is a bit strange. Don't worry about what it stands for. So this comp approach just says, okay, I've got some that are definitely non-defective. I'll just assume everyone else to be defective. Sorry, I'm writing negative and positive to mean non-defective and defective here. So yeah, it's kind of like, I couldn't rule you out as non-defective, so I'll just assume you're defective or infected or whatever you want to call it. The DD algorithm is meaning definite defectives algorithm is the other way around. It says, if I can verify that you're defective, I'll assume that you are. Otherwise, I'll assume that you're non-defective. And maybe the philosophy of DD makes a bit more sense because we're assuming defectivity is a rare property. So maybe the default assumption should be to assume maybe the default assumption should be to assume non-defective. But, it depends, like maybe in some applications you want, it could also depend on whether you care more about false positive or false negatives. If you want everyone who has COVID to really be identified that it's possible, then maybe you'd rather use this first algorithm. Okay, there are also more advanced algorithms. A like natural and basically optimal algorithm is actually an integer program. And integer programming is not that scary these days. Like Ruby can solve large instances pretty fast. But if it does get too computationally complex, especially in like large settings, you may want to relax it to a linear program. And then people have like used ideas borrowing from like coding theory, like belief propagation. So yeah, these tend to be like the best approaches, but it can be harder to get like type theory around them. Well, integer programming, you can get theory, but it could be like computationally difficult as well.
But there won't be problem.
Sorry?
If you use ID or LP, it won't be problem.
Well, we're still using like a random, we're still coupling these with a randomized test design, so that part is still probabilistic. Yeah. The decoder part is deterministic though. Yeah. Okay, so remember, like I said that these are results giving like how many tests these algorithms need. And remember, I'm plotting it in a indirect way, like n is the number of tests. But instead of plotting n, I'm plotting like the ratio of prior uncertainty to n. So like I'm kind of plotting how much information I learn per test. This first hardness result I said just gives you a straight line at 1. Like we can never go above 1 in this plot because we can't learn more than 1 bit per test. Oh, by the way, the x-axis is plotting like a measure of how many defectives we have. So like we have like number of defectives is like p to the power of a constant, and that constant is on the x-axis. So up here is like nearly linear number of defectives, and down here is like extremely rare or extremely sparse. Okay, so this simple pump algorithm, it gets the right scaling at least. It gets k-log p scaling, but the constants leave a fair bit to be desired. I mentioned this intuition that DD might be a bit more natural or like more reasonable, and the theory kind of confirms that. Like DD does outperform pump, like the one where you assume non-defective by default does do a bit better. Okay, so my entry into this field was this blue curve, but it wasn't a practical algorithm. It was like a very, very impractical brute force kind of thing. But you could see it did a lot better. It actually matched the impossibility result up to about a third, and then it came down and eventually matched the DD curve. Yeah.
All of these are just, well, I would call them upper bounds, but I guess they're lower bounds on the constant. Like you don't know that.
Yeah.
These are all possibility results. You don't know.
The black one is a hardness result. The rest are achievability results. Or, yeah. But I'll get to more on that in a second. So let's see. I think I'm going to come back to this curve. So yeah, this is like around 2016 what the picture looks like. That's using all this. This is all using that IID design. And a few slides later, I'll show you how these curves got improved by using a slightly better randomized design. With the better randomized design, we can actually get an exact threshold with a matching hardness result. So eventually we're going to complete this picture and get like the exact threshold. And through someone else's work, they managed to get it with a efficient algorithm. So like everything's kind of known, but not in this picture. Okay, so yeah, the information theory view I took I wasn't the first to do it. Actually, some of this was in the early Russian literature as well. But the early literature looked at like the very sparse, really, really sparse regime where k is a constant. And I was trying to get techniques that work when k is this like, p to the power of something, like this polynomial type of dependence. But the group testing problem does look a bit like a communication problem. Like you could think of this set you're trying to recover as a message, these like red columns as being a type of code word. Some channel produces your output. If it's noiseless, it's just a deterministic OR operation. And then you're trying to decode. So it looks a bit like a communication problem, and these tools from information theory come out to be really useful. In the flat part of the plot on the left, your result just comes out with this simple interpretation, like your number of tests you need is like your prior uncertainty, which you can measure with entropy, divided by like a mutual information, which is like how much you learn from each test. So yeah, in an ideal world, maybe the answer would always come out like this, but it's not that so simple. The answer comes out like this in the left part of the plot, due to some nuisances that come up with things like concentration bounds and other types of error events. Okay, so yeah, I'm talking about noiseless for now, but if you had a noisy channel, you could like bound this by some sort of channel capacity, and that's what we'll get to in the next part of the talk. So yeah, here's I don't know if I have much time to go into the analysis. Maybe like I'll flash up this slide in case anyone wants to read through it. The analysis is like loosely inspired by binary hypothesis testing and communication. So like in communication, if you want to figure out which code word was sent out of M options, you can look at this like log likelihood ratio, like what would the probability of my received sequence have been given that code word versus the unconditional one. So for the correct code word, this should be high. For incorrect code words, this should be small. And so if you try to like threshold it, you hopefully get the right answer. And the rest of the slide goes through some analysis. So, okay, you can basically do a bit of, for the incorrect ones, you can like get an m times e to the minus gamma type of bound and set gamma equals log m to make it small. For the correct code word, you can use like lower Flash numbers and mutual information comes out. So in the simple communication setting, you kind of get like log of number of options divided by mutual information, which is kind of related to that previous slide. So at a very high level, the group testing idea was similar, but a lot more difficult. Basically, you have to split all the error events based on how much that incorrect thing overlaps with the true one. So if your incorrect set is completely disjoint from the true one, it's kind of easy, like in channel coding. But if it starts to overlap, and if it overlaps more and more, it gets a lot more subtle. And the really high overlapping regime where you just like miss one or two things wrong, that gets really delicate. You have to get really sharp concentration bounds. Okay, so I'm not going to go into this, but just to give you a rough idea, it's inspired by communication, but came out to be a lot more difficult. Okay, so now going back to something a bit less technical. I mentioned that the previous plot was based on independently putting items in tests. The better design, the problem with that design is like, you could get a few items that are in an unusually small amount of tests. Okay, so, you know, you're doing things IID. If you do things IID like P times, some of those will be like unusually small, like the number in the test. So to sort of overcome that limitation, it turns out to be a bit better to just put everyone in the same number of tests. So every item goes in L tests. L is a parameter you can tweak. Everyone goes in L tests, and those are, say, chosen randomly. The most natural might be random without replacement, but with replacement turns out to be a bit easier to study. If you go in the same test twice, you just count it as a 1. Like, so yeah, with replacement, the math comes out a bit nicer. So here's the plot from before, and here is what we get when we switch to this more clever design. So the algorithm curves go up a bit. The information theoretic curve goes up a bit. And going back to that question, if you look at this flat part followed by going down the dashed blue curve, there's actually a matching hardness result for that. So basically, this is the ultimate threshold. At least this is the exact asymptotic threshold. It's 1 for a while, then it drops down towards 0 like this. And yeah, so now we know the exact limits of noiseless group testing. And yeah, this paper from the Frankfurt team actually managed to get a efficient design that meets it. But they couldn't just use this like simple random design. They had to use this spatial coupling ideas from coding theory.
When you say optimal among all designs, you mean no matter what probability distribution I choose on tests, and no matter how I choose.
Even non-random, just any fixed matrix, the best possible matrix you could come up with will still not get better than that threshold. So yeah, that's the limits of noiseless group testing. I'll just add one more thing, which is like, if you're willing to get a few things wrong, like if you relax your criteria so that I only have to get most of them right rather than all of them right, then things actually simplify a lot. You just get like a straight line at 1 the whole way through. So yeah, approximate versus exact recovery makes a big difference. For exact recovery, the curve comes down like this because, yeah, getting 1 or 2 wrong gets harder and harder. Okay, any questions on that?
So what is the gap between the solid blue and the dash blue?
That's the IID design versus the more structured design.
That actual fraction.
Well, all of these increases are from like, I forget exactly, like, this is log of 2, and this is like 1 on E times log 2, so this is about 0.53, and this is about 0.7. The increase is something like times 1.3 or times 1.3 something. They all go up by that factor, like blue, red, and green. I don't have, yeah, you can see the exact constants, but I don't have a very insightful thing to say about it. Okay, any more questions on noiseless setting? So next is noisy and non-adaptive. I'll go for like 10 more minutes or so. So I'll just show you the simplest noise model. Simplest noise is where, like, instead of this OR operation, you get OR, but then it gets flipped with some probability, like I'll call it rho. So think of rho as like a small constant, like 0.05. So every noiseless test gets flipped with probability 0.05. This may not be the most realistic because, you know, it may not be symmetric, or it may depend on how many defectors are in the test, but this is a reasonable starting point to keep things a bit simpler. So yeah, we can do that information theory approach as well, because information theory is really suited to noisy settings as well, like general probabilistic models. So instead of the counting bound, you get like a capacity bound. So, you know, passing something through a channel which flips with some probability is the famous like binary symmetric channel from information theory. And we know we know that there's some maximum information that can be passed through that. And, you know, such knowledge transfers directly to group testing. So we get, I think this noise level something like 0.01, and we get a threshold a bit below 1 because of the noise. And if you were to increase the noise, of course, this would come down further and further. Okay, so this noisy version of the simple comp algorithm, it comes out a lot less, you know, a lot lower down, like a much bigger gap. So a bit unfortunate for that one. For the information theoretic paper, I also did noisy, but again, it wasn't quite as strong. Like, you've only got this little tiny gap, tiny narrow part near the really sparse regime where you match the black curve. So, you know, overall, you might be sensing that, you know, noisy is usually not doing quite as well. Okay, so separate decoding is it's like a refined version of the green one. It does a fair bit better. You can extend that DD one, which had pretty good performance in the noiseless case, but again, it doesn't do quite as well as we hope. And yeah, this was the picture until maybe the end of last year. So overall, like, decent results, but definitely left a lot more to be desired compared to the noiseless setting, even for this simplest noise model. Okay, and sorry, there was one more paper in 2022 which did this like more structured design and lifted up this red curve. I think they lifted up the green curve as well, but maybe I forgot to plot that. So yeah, again, pretty reasonable analogous results, but we don't have like exact understanding like before. Just this year though, that has been closed quite a lot. 2 concurrent works by us and the Frankfurt team. So in our paper, we gave an exact threshold for the Bernoulli, for the IID design, that's this red curve. And we gave an exact threshold for the structure design, that's the blue curve. We didn't prove a universal hardest result, like we didn't prove that no design could do better, but we proved that at least this particular design can't do any better. So it's the exact threshold for the design that we're considering. We don't know whether it's optimal around all designs yet. So yeah, again, we used like very computationally expensive methods. So we were just getting the information theoretic limits without saying how to get them practically. But this concurrent work actually used that spatial coupling idea and got the same blue curve with an efficient method. So basically, following these works, they're both unpublished for now. Following these works, we now have like a much better understanding. The one big open question is like, you know, is this blue curve actually optimal among all designs rather than just among these particular designs? Okay, this was really tough. So yeah, we were like bashing our head against the wall for 6 months, and we thought we had something based on our earlier methods, but then we found bugs and then we fixed them, and we had to analyze low overlap and high overlap very differently. The high overlap had to be completely different from the noiseless case. And yeah, it's like, it's pretty remarkable how like no matter how niche your topic is or how hard the result is, there's always a chance this concurrent work, and that happened to be the case here. So yeah, now there's two papers. I think our results don't overlap a huge amount, but we both get this blue curve in different ways. And we use fairly different techniques as well. Okay, so I think that's all I'll say about noisy non-adaptive. Are there any questions? Yeah.
The noise parameter is fixed for this system.
This is like parameter 0.01, and we could plot it for other parameters. Actually, another thing that paper did better than us is they handled asymmetric noise as well, and we didn't, because it was already so hard to just do the symmetric noise. So yeah, those two papers, getting to be among, like, they could be really tough to read. Our paper is like 70 or 80 pages, so it was very tough. I think I'll skip over this. This is just outlining one of those techniques where we decode items separately. Just very briefly, like the idea of this simpler decoding rule was to just like look at one column at a time and check how closely it matches the outcomes. If you get a lot of ones in both, it's like good evidence that it's effective. You can turn that into an algorithm, and it does like good but not great. It gets this purple curve. Okay, and this is like sort of like the communication picture. Instead of one big communication channel, it's like looking at a bunch of them separately, but I think I'll skip over that. And I'll end with this noisy adaptive setting, which somehow got really overlooked. Like, noiseless adaptive was so well solved, and nobody or almost nobody looked at noisy adaptive. So yeah, in my 2019 paper, I tried to, give some additional understanding of this. And the approach I took was pretty simple. It was basically like, first use a non-adaptive design to get a pretty good answer, like to get something with not too many false positives and false negatives, like not too many things that are misclassified. And then perform some sort of cleanup, okay, to sort of fix the mistakes that you made in the non-adaptive part. So like, here's a picture, like say the black one is the true one. Your initial estimate is maybe the blue one. So you got 4 out of 6 correct, but the one on the left is a false positive. The one on the second to the right is the second to the right red circle is a false negative. It turns out to be like not that hard to correct these sorts of mistakes. So to correct for false positives, you can like do some individual tests on these. You need to do like more than one individual test to combat the noise, but with not that many individual tests, you can figure out, okay, I got this wrong. Maybe I should flip this back from defective to non-defective, like correct for the mistake. And to correct for false negatives, you can like take everything you thought was negative and treat it as like a really, really sparse problem, because like there's really few false negatives. So this just reduces to like another group testing problem, but it's a really sparse one. With a really sparse one, we don't need many tests to solve it. That's basically the idea. In a more recent paper, we used noisy binary search. Again, it feels like maybe someone should have thought of this earlier, because binary search was so successful in the noiseless case, and noisy binary search is a well-studied topic. So yeah, why not just use the same idea as before, but use noisy binary search instead of regular noiseless binary search. And yeah, that does work well. To get really sharp constants in the theory, we had to refine it using some of these cleanup ideas, but that's basically the idea of the algorithm. When we ran it experimentally, we didn't even need to do the refinements or whatever. Like, we just literally took a famous binary search, I think it was Karp-Kleinberg's multiplicative weights algorithm. We just used it in a very simple way, and yeah, we got quite a big reduction in the number of tests compared to the like state-of-the-art non-adaptive. Okay, any questions? Going a bit quickly at the end here.
You said not noisy binary search is well studied.
Yeah, I mean, it's not like a huge hot topic, but there's probably dozens of papers on it. Or I don't know, like I could probably name 5 to 10 papers on noisy binary search. Yeah.
But in this group testing or just not?
No, those are papers from like separate from group testing mostly. So like, yeah, noisy binary search is of independent interest, and there are various algorithms and guarantees for it. Yeah. Okay, and here's what the number of tests looks like. sorry, I should have updated the red curve. This is the red curve is the worst non-adaptive one, which has now been improved, so. But anyway, the point is to look at the new purple curve, which is what we get by being adaptive, and yeah, we get very significant gains. Unlike in the noiseless case, we don't have matching upper and lower bounds, but we have especially in the lower noise regimes, we have like a pretty good understanding, like the purple one can be achieved, and the black one is a hardness result that I derived. And yeah, there's some gaps to be closed, but a pretty good understanding. And adaptivity clearly helps. Okay, so I think that's the end. We have a survey on this from 2019. It's getting a bit out of date because like some of these newer results are not in there. With possibly thinking of updating it, but I can't promise that. So yeah, for now we have this 2019 version, which covers most of what I discussed today. Okay, and I'll end there. Thank you. Any more questions?
So what was the difference between the last two graphs?
This is two different noise levels. So if you set your noise, the famous tracing information theory is if you flip test with probability 0.11, you get almost exactly half as your capacity. So this line starts at half. This is that must be a really low noise. This must be like 0.001 noise because it looks like it's at 1, but it's actually a tiny bit below 1. Yeah. So it's kind of like a moderate noise on the left and a very low noise on the right. Yeah. Okay, thank you.